Hi, good evening. This is Math 2414. This is April the 4th. And so first of all, a few announcements. Exam 2 grades have been posted on your D2L website yesterday in your D2L gradebook. A couple of things to point out. Final exam replaces the lowest exam. So if you have 2 exam grades now, if one of those is not as good as you wanted to, you can always replace it with the final exam if it's higher. W-Day, I think I may have reported to you that it was Friday, April the 6th, but it's actually, I believe, tomorrow, April the 5th. So that's the last day to receive a W in a class. And as I would always recommend, please talk to me. You have several ways to get in touch with me. Talk to me about your grade if you have concerns about your grade. So you can get in touch with me using Remind or by sending me an email. And I'll be happy to talk to you about the status of your grade at this point of the semester. Exam 3 is coming up. The review for Exam 3 will be posted next week. And the window for taking Exam 3 opens on April the 19th. So that's 2 weeks from tomorrow, actually. And then finally, you do have homework due, weekly homework due this April the 8th. Thank you for all of you that have turned in homework yesterday. So that was your most recent daily homework. The review for that will be put up, or not the review, but the solutions to that will be put up relatively soon, hopefully tomorrow sometime. I will go ahead and put up the solutions to the homework. Remember, those always go on my Google site and in the section on syllabi, and so I'll always put the key to those up there. All right, and so again, the next homework assignment will be due April the 8th, and I'll talk about that again at the end of lecture today. All right, so let's pick up where we left off last time. Now, last time we were talking about sequences and series, so this is kind of an outline of what we're going to cover in class today. We're going to first go back and do a little bit of reviewing on sequences and kind of go back over and make sure that all that stuff is kind of tied together a little bit. And then we're going to finish our discussion on sequences today by looking briefly at the squeeze theorem and talking about how the squeeze theorem operates. And then after we deal with the squeeze theorem, then we're going to move on to infinite series and start talking about really the main idea for the rest of the semester, which is the idea of an infinite series and when an infinite series converges and when it diverges. So this is really different than anything you've covered in a calculus class. So if you've not done sequences and series, and this is your first time through this, you really need to pay attention to the lecture. You need to get online and email me or get on to my office hours and ask me questions. This is really important here, especially because this is very new material compared to a lot of the stuff we've been doing. I mean, the calculus stuff that we just came out of, I mean, I know it may have been difficult, but at the very least, we were talking about areas and slopes and tangent lines and derivatives and integrals, all things that you're familiar with. But here with sequences and series, it's really different. And so I want to make sure that you are kind of working on this and paying close attention to it, because it'll be an important topic on exam 3. It'll also be an important topic on the final exam. All right, so last time we were talking about sequences, and remember, so first of all, let's talk about some of the key words here. First of all, remember, you think of the word list when you think of a sequence, and you also think of a function where the domain is the counting numbers, is the natural numbers. Right, 2 different ways to look at kind of the same thing. So, and then if you talk about the nth term of a sequence, you could refer to it as S sub n, where S sub n describes the general nth term of a sequence. And so the sequence will look like this: S sub 1, S sub 2, S sub 3, S sub 4, and so on. Okay? And so what happens here is that the sequence converges if the limit as n increases without bound of S sub n exists, right? So if it is equal to some constant, then we say that the sequence converges. And then the sequence diverges if the limit as n goes to infinity of S sub n is equal to either plus or minus infinity, or simply just does not exist. Now, plus or minus infinity really kind of implies does not exist also, but there's other ways that a sequence might, or the other ways that a limit might not exist besides just having positive or negative infinity. There is as an answer. All right, so let's look at some examples to kind of go back over what we've talked about. So S sub n, if S sub n was given by this quantity, 2n plus 1 over 3n plus 4. Now remember, that is the general nth term of the sequence. Okay, so once again, let's write down S sub 1 then would just be, you just plug in 1 every place you see an n. Right, so in the numerator that would be 2 plus 1 over, in the denominator, 3 plus 4, and you get 3 over 7. S sub 2 would be 4 plus 1 over 6 plus 4, and so that'd be 5 over 10, or 1/2. S sub 3 would be 6 plus 1 over 9 plus 4, and so that'd be 7/13, and so on. Right, so our sequence in this case, the first three terms of the sequence then are 3/7, 5/10, or 1/2, and 7/13, right? And then that sequence would continue on like that. And so the question is, does this sequence converge? So I'm going to write converge and put a question mark there. Very simple. If you have the nth term of the sequence, that's a simple question. You simply look at the limit as n goes to infinity of the nth term. We talked last time about the fact that even though these functions were defined as discrete points, that we could still use L'Hopital's rule and other ideas that we've used for limits would still work for this type of a limit. So we're not limited, no pun intended there, but we're not limited by the fact that this is a sequence and that the graph of the sequence is a bunch of dots. We can still use those theorems and it would still apply. And so here, this is just infinity over infinity. You could, and then you look at the leading terms here, because it's a rational expression, you get 2n over 3n, and so you get 2/3. You could think about L'Hopital's rule if you wanted to and differentiate. Technically, remember what you're really doing with L'Hopital's rule is you're really looking at this real valued function, right? And you're looking at the limit as x goes to infinity. But see, when you do this, you're getting the exact same result. That's infinity over infinity. You can use L'Hopital's rule, and you get 2 over 3, and so you get 2/3 as the answer. So we had a theorem last time that said that these results would always be the same. So the way I'll look at this is I'll just kind of bypass that part of the argument and just go right to taking the limit of the nth term like I did here. Okay, so anyway, the limit does exist. And so what do we know here? That this sequence converges to 2/3. Now, one thing that you've got to get used to, and a lot of students are not used to this, is you have to tell me what your conclusion is at the end, and you have to spell it out in words. So don't just finish this with the limit equals 2/3 and then stop, because then you're letting me finish the argument by saying, hey, because the limit exists, the sequence converges, and I want you to finish the argument. So make sure that you finish this and you tell me that the sequence converges to 2/3. Otherwise, I'm probably just going to put a question mark on at the end of this problem and say, hey, does the sequence converge? You never told me, right? And I am going to penalize you for that on a test. So I want you, because I want you to be really clear about your arguments. most of you, well, all of you, you're in Cal 2, you have picked some type of a science or math discipline, engineering, biology, biochemistry, med school, math teacher, etc., computer scientist. All of you have picked fields like that where you have to be precise about what your conclusions are. And so you have to get used to writing those conclusions out. So I'm really going to kind of try to hammer that home in this last unit on sequences and series, okay? All right, let's look at another example. So we're just kind of going through some examples here of sequences just to kind of cement and tie together things we were doing last time. So let's say that this is the nth term of our sequence. S sub n is equal to 4 minus 1 over 2 to the n. And so once again, the question here is, does this sequence converge or does it diverge? And so once again, a direct approach to this problem is to take the limit of the nth term. So we're taking, we're taking the limit as n goes to infinity of 4 minus 1 over 2 to the n. And as n goes to infinity, notice that that last fraction right here, the 1 over 2 to the n, that's going to 1 over, and what's happening, the denominator is going to infinity. So that type of fraction, remember, always goes to 0. And so what happens here, this limit does, in fact, go to 4. Right? The limit does exist, and it's equal to 4. And so our conclusion here is that the sequence converges to 4. Remember that what that means is as you go further and further out into the sequence, the terms are simply getting arbitrarily close to 4. They're getting closer and closer and closer to 4, and you can get as close to 4 as you move out into the sequence as you want, right? All right, the next example we want to look at is S sub n is equal to 4/3 to the n. This type of sequence is in this general form of a times r to the n, and we call this a geometric sequence. We did talk about this type of sequence a little bit in last lecture. And what we saw was that a geometric sequence that's in this form, where it's just some r value raised to the nth power, that type of sequence converges depending on the r value. It converges if r is between -1 and 1, and it converges if r is 1 also. So, you know, in this particular problem, you could look at this a couple of different ways, but what's r here? R is 4/3, which is bigger than 1. And so what that means here, or what that implies, is that the series diverges. That's also really easy to see if you simply go ahead and list out some of the terms, right? S sub 1 is 4/3. S sub 2 is 16/9. Oops. S sub 3 is 64/27, and so on. And what happens, those terms are getting larger and larger, right? These are not getting smaller and smaller. They're not getting closer and closer to some number. They're just moving on and getting bigger and bigger, and they're going to get large without bound. They're going to get as large as you want them to be. And so what do we know here? That the limit as n goes to infinity of the nth term doesn't exist. It's actually equal to infinity. So what's our conclusion here is that the series and oops, I just went back and looked at a very bad mistake here. This is, I said series. I wrote that down, but it's a sequence that we're talking about here. Definitely not a series. And so the sequence diverges. All right, so basically if you have a sequence and you have an nth term of a sequence, look at the limit as n goes to infinity of the nth term of that sequence. If the limit exists, the sequence converges. If the limit does not exist, or it's equal to positive or negative infinity, then the sequence diverges. All right, so now let's talk a little bit about the squeeze theorem. The squeeze theorem basically goes like this, that if you have two sequences, well, three sequences ultimately, but you have two sequences, A sub n and B sub n, those are the general nth terms, and then you have another sequence that you're looking at that's S sub n, and you know that the S sub n's are always between the A sub n's and the B sub n's, like that. Then what's going to happen basically is what you're doing here is you're trapping this sequence that has an nth term given by S sub n. You're trapping it between two other sequences, right? And so if you can, a couple ways to look at this, but if what's going on here is that if the limit as n goes to infinity of A sub n is equal to m, and the limit as n goes to infinity of B sub n is also equal to m, then what has to be true here? Then it must be true that the limit as n increases without bound of S sub n is equal to m also. Right? That what you're doing is if you're trapping a sequence between two other sequences and those both approach m as n gets large, then the sequence that you're looking at has to approach m also. It's trapped between the two of them, and so that limit would have to be the same thing. This is also going to be true, isn't it, if, for example, if the limit as n goes to infinity of A sub n is equal to infinity, and S sub n is bigger than it, well, it's got to go to infinity also, you know. So that's another way to kind of look at it. So let's look at this sequence. So the sequence has an nth term given by cosine of n divided by n squared. And we want to decide whether this thing converges or diverges. So converge, and I'll put a question mark here. All right, so, you know, you could kind of reason through taking the limit here, but let's nail this down a little bit better by actually looking at using the squeeze theorem here. If we let A sub n equal negative 1 over n squared, that's its nth term, and B sub n is equal to positive 1 over n squared. So you see that cosine of n is always trapped between negative 1 and 1. So notice what has to be true here then is that the cosine of n over n squared is got to be trapped between negative 1 over n squared and positive 1 over n squared. Because cosine of n is trapped between negative 1 and 1, this has got to be true, that this expression's got to be trapped between those two like that. All right, and so what do you know about the limit as n goes to infinity of negative 1 over n squared, and the limit as n goes to infinity of positive 1 over n squared? Well, in both cases, you're going to get what? Negative 1 over infinity, that's approaching, or 1 over infinity for that one. In either case, those types of limits we know always go to 0. So what's got to be true? The limits of those two known sequences on the outside of that inequality both go to 0. And so what has to be true about that sequence that's trapped between them? It's got to go to 0 also. It's got to do the same thing. So our conclusion is that the limit as n goes to infinity of cosine of n over n squared goes to 0 also, and this is by the squeeze theorem. And so what's true? What's our conclusion here? Our sequence, almost said series again, our sequence converges. And in fact, it converges to 0. Okay, so I don't want to make a too big a deal about the squeeze theorem. I think it's a nice little theorem to know. It's something you can fall back on if you get in trouble on a sequence, and then in other situations also. But it's not in the grand scheme of things, it's not a hugely important idea for us. But it's something that's a good to know kind of thing. All right. So now we're going to move on past sequences, and we're going to move on to the main event for the semester, for this chapter, for this last unit here, and that's the idea of a series. And in particular, we're talking about an infinite series. All right, so first of all, a little bit about notation. Now, and by the way, a series is referring to a sum. This is an infinite sum that we're talking about, an infinite sum. So the notation that we frequently use is we frequently use what we call sigma notation for an infinite series. That's my Greek letter sigma right there. It's the best I'm going to be able to do. And so you have a counter on that sigma. When you see a sigma in mathematics like this, you're talking about a sum automatically. And then you've got an index on the sum, and that index it counts literally from n equals 1 to infinity. So it's n equals 1, n equals 2, n equals 3, and so on. And then the general nth term of the series we'll refer to as a sub n. So this would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and so on. Right? That's the type of problem we're talking about. That's what a series is right there. So just as an example, if you're talking about the sum as n goes from 1 to infinity of, let's say, 2 to the n over 3 to the n minus 1. All right, so what would that series look like? That would be, when n is 1, you'd get 2 over 3 to the 0 is 1, so you get 2. Plus, so that's when n is 1. When n is 2, you'd get 4 over 3. That's when n is 2. When n is 3, you'd get 8 over 9. That's when n is 3. And so on, right? That's the notation we would use, and that's what we're talking about here, is an infinite addition problem, right? Where you're adding an infinite number of terms together. All right, associated with every infinite series is something called the sequence of partial sums. We kind of referred to that last time in our last lecture. It's called the sequence of partial sums. And the sequence of partial sums, now this is a sequence, and so this is a list. But associated with every series, we have this list, or this sequence that's associated with it. And this is how you get the terms of the sequence. The first term of the sequence, which we'll refer to as S sub 1, is just the first term of the series. The second term of the sequence is the first two terms of the series added together. S sub 3 would be a sub 1 plus a sub 2 plus a sub 3. And so on. S sub n, which is what we call the nth term of the sequence of partial sums. Right, that's what S sub n is. That would be the first n terms of the series added together. So you'd go all the way out and add up all the way up through a sub n. And it's pretty clear cut as far as how a series converges. Right? A series converges and therefore has a sum if the limit as n goes to infinity of S sub n, and S sub n is the nth term of the sequence of partial sums, if that is equal to S, in other words, it exists. And the sum of the series would be equal to S. Whatever that S is, whatever the value of that limit is, that would be the sum of the series. And so that sounds very, very simple overall. You get a series, you get this list that's associated with the series that's called the sequence of partial sums. You take the limit of the nth term of the sequence of partial sums. If it exists, the sum exists. The series converges. Easy, easy, easy. The problem is you have an infinite series. You're given an infinite series. You almost never can, or it's very seldom that you can actually write down an expression for the nth term of the sequence of partial sums. You can in some cases. We're going to look at those at the beginning. But in most cases, you can't actually write down an expression for the nth term of the sequence of partial sums. And please do not confuse A sub n with S sub n. A sub n is the nth term of the series. That's one thing, and you're going to typically be given that in a problem where you're looking at a series. S sub n is the nth term. Let's see, the nth term of the sequence of partial sums. And like I said, you almost never are going to know that is the problem. And so frequently we are going to not be able to use that statement at the very end to decide whether a series converges or not. We're going to have to do it indirectly rather than directly. All right, and so we're going to give you a good overview of how this works out with a couple of examples, so that you, in your head, you've got a clear distinction between the nth term of the series and the nth term of the sequence of partial sums. By the way, the other thing I didn't finish on that last screen, but the series diverges if the limit as n goes to infinity of S sub n, which is the nth term of the sequence of partial sums, does not exist or is equal to plus or minus infinity. Okay, so that tells you how a sequence converges. It converges if the limit of the nth term of the sequence of partial sums exists. The series diverges if the limit of the nth term of the sequence of partial sums does not exist, or it's infinity. All right, so let's look at an example. Where here's our series. The series is the sum as n goes from 1 to infinity of, and actually let's start this one just to make it a little bit different. Let's start this one at 0 and go 0 to infinity. You can actually start a series wherever you want. You don't have to start it at 1. You can start it at 0. You can start it at -2 or -3. It has to be started at an integer for sure. So. Okay, the sum as n goes from 0 to infinity of 1 over 2 to the n. Okay, so we start this counter at 0, and when n is 0, you get 1 as the first term. When n is 1, you get 1/2. When n is 2, you get 1/4. When n is 3, you get 1/8. N is 4, you get 1/16. And so on. There's our infinite series listed out as an addition problem. All right, so let's look at this sequence of partial sums. Now, 1 over 2 to the n, that's A sub n right there. That's the nth term of the series. That's A sub n. But now what I'm doing is I'm looking at the sequence of partial sums, and so I'm going to try to head towards S sub n, which is the nth term of that sequence. So let's have a look at this sequence. S sub 1, the first term of this sequence, is just the first term of our series. The second term of this sequence is the first two terms added together. The third term is the first three terms added together. The fourth term, I'm going to go out at least to the fourth term here, is the first four terms added together. The nth term of the sequence of partial sums is the first n terms added together. So you write dot, dot, dot out to 1 over 2 to the n. And the problem is that form right there is not something you could take the limit of. So if you're trying to take the limit of the nth term of the sequence of partial sums, you could not use that expression because it doesn't have a defined length. It's not a closed quantity in any way whatsoever. All right, now let's see what we got here. So S of 1 is 1. That's our first term of our sequence. S of 2 is 3 halves. Just add those two terms together, you get 3 halves. S of 3 is 7 fourths. S sub 4 is 15 eighths as you go through and add those terms together. So our sequence looks like this. It's 1, 3 halves, 7 fourths, 15 eighths. And what ends up happening here, you know, the first one, this first term is when n is 1. And then this is when n is 2, n is 3, n is 4, like this. Right, and so what ends up going on here is that, what I'm going to do here, let's see, I want to just change things just a little bit right here. Since I started my series with n equals 0, I want to start the sequence at n equals 0 also. So let me erase those subscripts there. I'm going to change those to 0, 1, 2, 3, and so on. And I think that will make it a little bit more consistent, which I wanted to pause there and make sure that this is a little bit more consistent here. So that's n equals 0, n equals 1, n equals 2, n equals 3, and so on. So what I want you to know is that there's a pattern here to this, and that every one of those terms follows this pattern, that the denominator is simply a power of 2, and it's 2 to the nth power. 2 to the 0, 2 to the first, 2 to the second, 2 to the third, so on. And that the numerator is always 1 less than twice that number. So it's 2 times 2 to the n minus 1. And so the nth term of the sequence of partial sums has a pattern to it. The nth term, or let's not even say the nth term, the terms of the sequence of partial sums follow a pattern, follow a well-defined pattern. And this, let me point out here at the end here, this rarely happens. This rarely will happen. In other words, we're not always going to be able to find this nice little well-defined pattern here. And I've got this pattern here, and notice that this is really 2 times 2 to the n over 2 to the n minus 1 over 2 to the n. And so the 2 to the n's divide out, and you end up with 2 minus 1 over 2 to the n. A really simple expression for the nth term of the sequence of partial sums. S sub n is 2 minus 1 over 2 to the n. Now let's compare here. Notice that this up here at the top, this is the nth term of the series. That's my a sub n. That is different than the nth term of the sequence of partial sums, which is s sub n. And which one are you looking at as far as deciding whether the series converges or not? Well, you're looking at the nth term of the sequence of partial sums. And notice that this is very simple to do. The limit as n goes to infinity of 2 minus 1 over 2 to the n. We just looked at a limit like this a few minutes ago. The 1 over 2 to the n goes to 0 as n goes to infinity. And so this limit is 2. So the nth term of the sequence of partial sums is equal to 2. And so what that implies about our series is that that's the sum of the series, right? Let's see, since the limit as n goes to infinity of s sub n is equal to 2 from below, then the series converges and its sum is 2. So in other words, this infinite sum right here is exactly equal to 2. I'm not saying it's approximately equal to 2. I'm saying it's exactly equal to 2. The sum as n goes from 0 to infinity of 1 over 2 to the n is equal to 2. Identically equal to 2. It's not close to 2. It's exactly equal to 2. So how do we get this result? Let's go back over this again before we leave this screen. We started with a series. We wrote out the terms of the series. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And then from those terms, we wrote out the terms of the sequence of partial sums. And then once we got the terms of the sequence of partial sums, we saw that there was a well-defined pattern to the nth term of the sequence of partial sums. We were able to take the limit of that nth term of that pattern as n goes to infinity. And we saw that that was equal to 2. And so that meant that the series converged to 2, that the sum of the series was equal to 2. Now let me point out again that the critical step here is that we were actually able to get a nice well-defined pattern to the sequence of partial sums. I put a box around at the very bottom of the page there. That's the step that rarely happens and we'll rarely be able to do. And so we're going to have to find other ways to find whether a series converges or not that are more indirect. All right, we will definitely come back to that type of series in a minute. So let's move on to another example. Another series, the sum as n goes from 1 to infinity of 1 over n. This series is actually so important in applications and in what we're going to be doing in this chapter that it actually has a nice name. This is called the harmonic series. And if you look at, if you write out the terms of the harmonic series, this is just 1 plus 1/2 plus 1/3 plus 1/4 and so on. All right, and so if we, let's look at the partial sums. Just like I did in the last problem, I want to look at the partial sums. So S sub 1 is just 1. S sub 2 would be 1 plus 1/2, which is 3/2. S sub 3 would be 1 plus 1/2 plus 1/3. So you're just taking the two terms below and adding 1/3 to it, and you end up with 11/6 right there. S sub 4 is 1 plus 1/2 plus 1/3 plus 1/4. So you're just adding 1/4 to 11/6, and you get 25/12. S sub 5 would be 1, and this is the last one, so don't turn off the video yet. This is the last one I'm going to write like this. So now you're just adding 1/5 to 25/12. And when you do that, you get 137 over 60. You could continue on with this, you know, S sub n would be 1 plus 1/2 plus 1/3 plus ... out to 1 over n. Now, the question is, can we get a closed form for the nth term of the sequence of partial sums? So if you list out the sequence of partial sums, you get 1 3/2, 11 6, 25 twelfths, 137 over 60. And what ends up happening here is there is no well-defined pattern. I'm going to tell you that that's true right now. So, what ends up happening? Well, as it turns out in this particular problem is that these terms just get larger and larger without bound. Now, it gets slower and slower, but the deal is you give me a number, and I will always be able to go out far enough into the sequence of partial, I'll be able to go out far enough into the sequence of partial sums to get a sum that's bigger than the number you give me. So like you give me 1,000,000, and I'll be able to add up enough of these terms in the harmonic series so that the sum is bigger than 1,000,000. You give me 10 million, I can still do it, and so on. And so the limit as n goes to infinity of s sub n is equal to infinity here. I did not prove this. I'm just telling you this is true right now, but I haven't proved this by any means. And so you have to take my word for it at this point. We will prove this later. We will prove this. There is a proof in the book in this particular section, but I think it would be just best to just hold off on that for now. You're not going to get a lot out of that proof, I don't think. We're going to hold off on how we do this until another day or two. We will prove this statement later. But for our purposes, I'm telling you right now it's true that the limit of the nth term of the sequence of partial sums for the harmonic series is equal to infinity. And so the harmonic series, the conclusion here then is that the harmonic series sum as n goes from 1 to infinity of 1 over n diverges. Maybe an unexpected result, but it's definitely true, as it turns out, that this is a divergent series. Now, one thing I want you to note is that if you took the limit of the nth term of the series, here's the nth term of the series. If you took the limit of the nth term of the series as n goes to infinity, you do get 0. And notice that doesn't mean anything in this problem. So this clearly doesn't tell us anything. This clearly then is not enough for a series to converge. We're going to talk more about this in a few minutes, but I wanted to point this out right now, that just because the nth term of the series goes to 0 does not tell you that the series converges. Here's an example of the harmonic series, where the nth term of this series gets smaller and smaller and smaller, but when you look at the sums just get bigger and bigger and bigger. All right, so now, before we go any further with talking about the convergence of series, let's talk a little bit about algebraic properties of series, of convergent series. So algebraic properties of convergent series. So let's start off by assume that you have two series, A sub n and B sub n, and both converge. So in other words, both have a sum. Then what ends up happening is that if you look at the sum as n goes from 1 to infinity of A sub n plus B sub n, then it would be legal in this case, if both of those individual series are convergent, that you can evaluate that by looking at the sum of each series individually, like this. And that statement holds true for subtraction as well. If the series that you're starting with is a sub n minus b sub n, in other words, the series you're looking at are two convergent series that are being subtracted, then you can just find the sum of each individual series and subtract their results. But that's legal to do. And then finally, a third algebraic property that's nice to know is that if you have a series that you know converges, like a sub n, and it's being multiplied by some constant, then you can actually take that constant and factor it out of the series, just like you would out of a polynomial, and take the constant outside of the sum, and then just evaluate the sum that converges and then multiply by c at the end. That's a legal thing to do. So those are nice algebraic properties. So the good news here is that series that are convergent, the algebra on those is pretty straightforward. You can add, subtract, and you can multiply by a constant with no problem at all. So that's very beneficial that we can do that. That'll be super helpful. All right. So now let's talk about our first category of our first actual category of series, and we call this a geometric series. And a geometric series is generally a series that can be written like this. The sum as n goes from 1 to infinity of a times r to the n minus 1. R is a constant. R is a constant, and it is called the common ratio. All right, and then the a value, notice, is the first term of the series. It's the first term because the first term is when n is 1, and notice when n is 1, you've got r to the 0 power, and you're left with a there. All right, if you write out the terms for this series, notice what you get here. When n is 1, you just get a. When n is 2, you get a times r. When n is 3, you get a times r squared. And then a times r cubed, and so on. So notice that this geometric series is one where the common ratio, that term, comes from the fact that if you divide successive terms, you always get r. In other words, if you just multiply one term by r, you always get the next term. Right? You multiply by r, you get the next term. You multiply by r, you get the next term. You're always just multiplying by the same number to get from one term to the other. And this is called a geometric series when that happens. All right, so the question is, when does a geometric series converge? That's our question. And so, or for what values of r? So we're gonna kind of derive this result, and then we're going to look at a bunch of examples. So if you're watching this video, we're going to actually work through some examples here, definitely several examples, so that you can see how geometric series work. And this is the most basic type of series that we're going to look at. All right. So let's look at the nth term of the sequence of partial sums for a geometric series. So let's say we have this geometric series. N goes from 1 to infinity. You have a times r to the n minus 1. So s sub 1 would just be a. S sub 2 would be a plus a times r. S sub 3 would be a plus a times r plus a times r squared, and etc., right? And so the nth term of that sequence of partial sums would be a plus a times r plus a times r squared plus dot 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 out to, and notice on the nth term, the power on the r is always 1 less than the term you're at. So this is going to be a times r to the n minus 1 right here. That's our nth term of our sequence of partial sums. It's not a closed form at all. And so the question is there a way to kind of do some tricky little arithmetic to get a closed form here? And it turns out that there is. So now take that nth term and you multiply it by r. So when I multiply that by r, you're just multiplying every term by r right there. And so when I multiply every term by r, I've got a times r plus a times r squared plus a times r cubed plus, and I'm going to write the last two terms down here. This would be a times r to the n minus 1, and then there would be this last term, a times r to the n. Right? You're multiplying every term by n here. By r. And so when you multiply every term by r, you know, like this last term has n minus 1 r's in it. When you multiply by r, now you have n r's. So that's our last term. And so now what we're going to do is I'm going to draw a line under those, and we're going to actually subtract term by term. So you get s sub n minus r times s sub n equals, and now notice when you subtract, the ARs, the AR squares, the AR cubes, all of those terms cancel out when you subtract, except for the A at the very beginning and the a times r to the n at the very end. So this is a times r to the n here at the end. Everything else subtracts out. So that's helpful. So on the left side, you factor out the s sub n, and you're left with 1 minus r. And on the right side, you could actually factor out the a, and you're left with 1 minus r to the n. And then you divide here, and you do get a nice little expression in terms of n for the nth term of the sequence of partial sums. And so now remember, what you want to do here is you want to take the limit as n goes to infinity of this nth term of the sequence of partial sums. So when you do that, when you take the limit of the nth term, you're taking the limit on both sides there, and on the right side there, when you're taking the limit as n goes to infinity, what ends up happening is that when the r value, when this term right here, as n gets large, if r is between -1 and 1, then that term's going to go to 0. So when r is between -1 and 1, then the limit as n goes to infinity of s sub n is just going to be equal to a over 1 minus r, because that little r to the n is going to go to 0 in there. And as it turns out, when r is either bigger than 1, bigger than or equal to 1, or when r is less than or equal to -1, then the limit as n goes to infinity of s sub n is either does not exist or is going to be equal to positive or negative infinity. And so what do we have here? We kind of derived the result here that a geometric series is going to converge when the r value is between -1 and 1. That should say 1 right there. -1 and 1. And it diverges otherwise. So let's write that result on the next screen here. So when you have a series in this form, n goes from 1 to infinity of a times r to the n minus 1. This is what we call a geometric series, an infinite geometric series, to be technical about it. And it converges if the r value is between -1 and 1, and the sum s would be equal to a over 1 minus r. and the series diverges if r is bigger than or equal to 1 or r is less than or equal to -1. All right, so that's a nice result. It ends up being a nice, clean result, as it turns out, and super, super important. You're going to see geometric series frequently in several different contexts through the rest of the chapter, through the rest of the stuff on sequences and series. So this is important that you know these ideas here. All right, so now let's look at some examples of geometric series. Let's see how this works out. So you have the sum as n goes from 1 to infinity of 3/5 to the n. All right, so what do you have here? You have certainly that this series is got this constant to a power. That's what you're really looking at, is do you have a constant to a power that involves an n like that? And you do here. And so this series is geometric. So this is what I'd want you to write down. That's geometric. And that the r value is 3/5. That's the constant that's raised to the power there. So that's going to be 3/5. What do you have here? That r is between -1 and 1. And so that tells you that the series converges. And that the sum of the series, don't have to go through a lot of angst to get to this. We have a nice little formula to calculate the sum of the series. It's just simply a over 1 minus r. Remember that a is the first term of the series. Don't forget that it's the first term of the series. So the first term of the series in this case is going to be 3/5. And then, so this would be 3/5 over 1 minus 3/5. R is 3/5 there. So you get 3/5 over 2/5 or 3/2. So you get that the sum of the series is 3/2. So this infinite series actually has a sum, and it's exactly equal to 3/2. Not approximate again. Remember, you're not talking about approximate here. You're talking about that this is exactly equal to 3/2. So I could write here at the end that this infinite series is exactly equal to 3/2. Okay, let's look at another example here. Like I said, we're going to look at several examples. So you see several different situations. So this is the sum as n goes from 1 to infinity of 3 times 2 over 5 to the n. All right, so you have to pay attention to what is being raised to the nth power here. And notice the only thing that's being raised to the nth power is that 5 in the denominator. So first of all, you have the sum as n goes from 1 to infinity. And you can just take 3 times 2, because the 2 is not being raised to a power. So this is just 6 over 5 to the n, first of all. And so you could factor out the 6 there, and this would be 6 times 1 over 5 to the nth power. And so there is a nice, better version, a nicer form for the nth term here for this geometric series. So this series is geometric. The r value is 1/5. R is between -1 and 1. And so this series converges. And then the sum of the series, now again, be really careful here. The sum of the series is S equals A over 1 minus R, but A is the first term of the series. So when n is 1 in this case, the first term of this series is going to be 6 times 1/5 to the first, be 6/5. So you have 6/5 over 1 minus 1/5. And so you get 6/5 over 4/5, which is 6/4 or 3/2. And so the sum of the series is 3/2. It turned out that 3/2 was the sum of the series in the last problem also. Obviously, that's not always going to be true. So the sum of the series in this case is 3/2. These will be things I'll be looking for. I'll be looking for you to tell me that the series converges. In words, I'll be looking for the sum of the series. I'll also be looking for you to tell me that the series is geometric, right? And what the R value is, that the R value is between -1 and 1. So in a geometric series like that, I'd want you to tell me it's geometric, tell me what the R value is, and why you're saying that the series converges, and then if it does converge, tell me the sum. All right, the next problem, you have the sum as n goes from 1 to infinity of 4/3 to the n. So in this series, it's also geometric, certainly, and we already have the constant raised to a power. So that's good. So we get right away that the R value, the common ratio, is 4/3. But in this case, what do we have? That R is bigger than or equal to 1, certainly. And so right away, I simply say that this series diverges, and I'm done with the problem. There's nothing else to do. There is no sum that exists. So no sum exists here because this series diverges. That just means that the terms of the sequence of partial sums just get larger and larger and larger forever. All right, the next sum I want to look at, or the next series I want to look at. So let's see, we have the sum as n goes from 1 to infinity of -1 to the n plus 1 times 3 over pi to the n. Okay. So this is what we call an alternating series, an alternating geometric series, actually, because the terms alternate positive and negative, which is okay. There's no problem with that. But it's something that you need to be aware of. So it's called an alternating geometric series. And so, well, what is the R value here? You know, there's a couple ways you could look at this, but if you want to, you could think about it this way. You would not have to do this, but this is one way to deal with this, is you've got -1 to the n plus 1, but you have 3 over pi to the n. So if you wanted to, you could take one -1 away from the -1 to the n plus 1, and then you'd have -1 to the n right there, times 3 over pi to the n. And so then notice that would give you -1 times, and then this would be -3 over pi to the n. Right? And so now you've got that kind of combined into one factor. And so what's the R value here? The R value is -3 over pi. Notice with an alternating geometric series, the R value will always be negative. When R is negative, you get an alternating geometric series. That's always true. So what about -3 over pi? Well, pi, remember, is 3.14. So this R value is between -1 and 1. And so what's true here? This series converges. And the sum of the series is A over 1 minus R. All right, so remember, A is the first term. So when n is 1, that's our first term here. You get -1 squared, and then you, which is +1, times 3 over pi to the first power. You get the first term to be 3 over pi. And in the denominator, this is going to be 1 minus, be careful, R is negative, so 1 minus -3 over pi. Like that. Now that's kind of a little bit of an ugly expression. I'm not going to find a decimal there. I'm just going to simplify this. I'm going to multiply top and bottom by pi, and you get, let's see, what do we get here? That S is equal to 3 in the numerator over pi plus 3 in the denominator. And so here the series converges, and the sum is 3 over pi plus 3. All right, so a little bit different type of problem, that's for sure. All right, let's look at one last problem here where the arithmetic is definitely not obvious at all. It's a geometric series, and then we have a couple of other things to talk about here. Wanted to check my watch and make sure we were doing okay on the time. We have a couple of other things to deal with here. So you have the sum as n goes from 1 to infinity of 3 to the 2 over n over 2 to the 3n plus 1. Yikes. Like that. So just looking at this may not necessarily be obvious. It's probably geometric because of the way it's written. You've got constants raised to expressions that involve n, so this is going to be geometric. But the question is, what's the r value? So you got to do a little bit of rewriting here on this expression. And so let's just take this expression and just look at that off to the side here, just below. You have 3 to the 2 over n to the 2n over 2 to the 3n plus 1. First of all, in the numerator, 3 to the 2n is the same thing as 3 to the second to the n. And in the denominator, 2 to the 3n plus 1 is really 2 to the 3n times 2 to the first. Just using rules of exponents, right? When you multiply like bases, you add exponents, so that would have to be true. So in the numerator, I get 9 to the n. In the denominator, I do the same thing with that 2 to the 3n. That's 2 to the third to the n times 2. So you have 9 to the n over 8 to the n times 2, like that. And so you end up with 1/2 times 9 over 8 to the n, like so. And so notice that that means I can take this series up here and write the nth term as just 1/2 times 9/8 to the n. And so you get here that r, the common ratio here is 9/8, and r is bigger than 1, bigger than or equal to 1. And so the series diverges. The key here is you've got to be able to identify a constant to the nth power like that, and then you can get the common ratio. I mean, first of all, that tells you that the series is geometric. And then you can get the common ratio, and then you can go from there. All right. The next thing we want to talk about is a theorem that leads to another way of looking at series that are not necessarily geometric. So we're going to leave geometric series behind just a little bit for a second. If the sum as n goes from 1 to infinity of a sub n converges, then what must be true, then what has to be true is that the limit as n goes to infinity of a sub n has got to be equal to 0. So it's said, what this is saying is if you have a convergent series, the nth term has to go to 0. Right? If you have a convergent series, then the nth term goes to 0. Now, that may be well and good. It makes sense that if you've got a convergent series that the nth term is getting smaller and smaller. But the key here is what this does not say. This theorem does not say that if the limit as n goes to infinity of a sub n equals 0, then the series converges. It does not say that at all. And in fact, we already know from the harmonic series that that statement is not true. You know that what you have here is this theorem over here is in a classic if P then Q form here. That if you've got this statement, P, is true, then Q has to be true. If P then Q is not equivalent to if Q then P. It is not, those are not equivalent statements. All right, that's called the inverse there, and those statements are not equivalent. However, what is equivalent goes like this, that if P then Q, if you have a statement like that that you know is true, and we have this theorem at the top here that we know is true, that it's in the if P then Q form, then this statement is also equivalent. Not Q, if not Q, I should say that. If not Q, then not P. In other words, if you negate the second statement, then that does imply the negation of the first statement. Now, I know that sounds really complicated here, but look. In our theorem at the top here, you've got, here's the statement P right here, if the series converges. Right, that's our statement. The series converges is our P value here. And then the limit going to 0 is our Q. Right, there's our Q. And so we have an if P then Q. What's equivalent to that is if not Q, then not P. So in our problem, or in this particular theorem, that means that if the limit as n goes to infinity of a sub n is not equal to 0, then the series as n goes from 1 to infinity of a sub n diverges. Now that is a theorem that we can use at the very bottom there. In fact, that is an important enough theorem that this version of that first statement here, that we're going to copy that and put it on the next page, and we're actually going to call it something. This is sometimes called the nth term test for divergence. It's called the nth term test for divergence. And what this says is, okay, so let me highlight that first of all, that name. It's called the nth term test for divergence. And what this is saying is that this is a test to prove that a series diverges. Not that a series converges, but that a series diverges. And what this is saying is, if you can take the nth term of the series and show that it does not go to 0, then it's got to be the case that that series has got to diverge. All right, so let's look at an example here. All right, so we're going to look at this series. The sum as n goes from 1 to infinity of 4 minus 1 over 2 to the n. Now that should look familiar to you because we looked at a sequence earlier in class today, earlier in the lecture, that had that nth term. The sequence had that nth term. This is a series now, and notice what happens here. Using that nth term test like I wrote above, if I take the limit as n goes to infinity of this nth term, I get 4, which is not equal to 0. So by the nth term test, I'll let you say it that way, by the nth term test, this series diverges. It does not have a sum. Now please do not confuse with a sequence. Do not confuse with a sequence. A sequence is a different beast here altogether. So if you have the sequence S sub n, notice there's no sigma here. If I have S sub n is equal to 4 minus 1 over 2 to the n, right, the limit as n goes to infinity of this sequence is equal to 4. And so this sequence converges, right? Because that's all that matters. That's all that you have to show for a sequence to converge, is that the limit of the nth term exists. But we are not talking about sequences anymore. We are talking about series. And it ain't that easy for a series. So if you can show that the nth term of a series is not 0, then by the nth term test, the series has got to diverge. Don't confuse that again with a sequence. All right? So let's say we have the sequence given by this. S sub n is equal to 1 over n, right? The limit as n goes to infinity of S sub n is equal to 0, right? The limit as n goes to infinity of 1 over n is 0. So what do we say here? That this sequence converges to 0. On the other hand, when you look at a series, the sum as n goes from 1 to infinity of 1 over n, right? A different beast. This is a sum. This is a series here. The limit as n goes to infinity of the a sub n, the 1 over n there, and I'll just write 1 over n, does equal to 0, but this says nothing about convergence. In fact, we know that this is the harmonic series and it diverges, even though the nth term goes to 0. So remember, with the sequence, it says everything when you can take the limit of the nth term. For a series, just showing that the limit of the nth term goes to 0 doesn't tell you a darn thing about the series. All right, we have one last type of series to look at. So we've looked at two things so far, geometric series and the nth term test, as far as talking about series now. So let's talk about what we call telescoping series. So a telescoping series might look like something like this. The sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 1, like that. That would be an example of what we call a telescoping series. Now, to look at the convergence of this series, let's look at the nth term of the sequence of partial sums, S sub n. Remember, this is the nth term of the sequence of partial sums. So when n is 1, you get 1 over 1 minus 1 over 2 plus, right? Because it's a sum, so we add. When n is 2, you get 1 over 2 minus 1 over 3 plus, because it's a sum. N equals 3. When n equals 3, you get 1/3 minus 1/4 plus, I'll go one more, n equals 4. When n is 4, you get 1/4 minus 1/5 plus, now dot, 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 and I'm going to go out to the, to not the last term, but the next to last term. So the next to last term would be the n minus first term, and that would be 1 over, so every place you see an n, you put n minus 1. So this would be 1 over n minus 1 minus 1 over n minus 1 plus 1, which would just be 1 over n. That's the nth term, or the n minus first term. Plus, and then finally, the very last term is the nth term, and that would be 1 over n minus 1 over n plus 1. So you expand this sequence, the nth term, out like this. And this is the nth term of the sequence of partial sums, right? This is the nth term of the sequence of partial sums. We're adding the first n terms together. Now I want you to step back and notice that what ends up happening here is that this thing collapses on top of itself. Because look, the negative 1/2 and the positive 1/2 add to give 0. And then the negative 1/3 and the positive 1/3 add to give 0. And then the negative 1/4, and the positive 1/4 add to give 0. All these terms are going away. And in fact, this continues on at the very end also. The 1 over n's go away. The 1 over n minus 1 is going to go away. And what you end up with is, notice, it just collapses completely. And the nth term of this sequence of partial sums just ends up being this really nice expression, 1 minus 1 over n plus 1. The very first term and the very last term survive this expansion. And you get the nth term of the sequence of partial sums in a nice closed form where you can take the limit. And so the limit of the nth term of the sequence of partial sums, it ends up being equal to, as n goes to infinity, that fraction goes to 0, and you end up with 1. And so what happens here is that the series converges, and the sum is 1. Now, you have to have an expression kind of like the 1 over n and 1 over n plus 1 in the expression. And so with the telescoping series, you expand it out like I did. You expand out the nth term of the sequence of partial sums. In other words, you add the first n terms together. And what ends up happening, if it's actually truly telescoping, is that it collapses. A lot of the terms cancel out, and you're only left with a couple of terms, in this case, one term at the beginning, and a couple of terms, in this case, one term at the end. All right, and so that's, I wanted to go through that. Again, not a major type of series, but it is a type of series we want to talk about. So today, what have we done? We've looked at geometric series. When a geometric series converges or diverges, and if it converges, we found the sum. We've talked about the nth term test for divergence to show that the nth term does not go to 0. And now we've talked about telescoping series. So we are on our way now as far as talking about infinite series and when they converge and diverge. So we've talked about 3 ideas here. So what we'll do next Monday is we'll continue on with this discussion of different types of series and how to tell when they converge or diverge. So that will be our next goal for next week. All right, so your homework, it's due April the 8th. I had already signed a couple of these problems. So this is section 5.1 in your book, problem number 2 and 50. And also in section 5.2, problems numbers 90 and number 102. Now, I'll tell you right now, number 90 is a geometric series, and problem 102 is a telescoping series. And you're trying to decide whether those converge or diverge. All right, so everybody have a great week. Have a great weekend. Work on this homework. I'll send you a remind message out to remind you about the homework. But try to keep up, please keep up with the homework. So some of you have got really good weekly homework averages. Some of you have weekly homework averages that are maybe not so good. Remember, that is 20% of your final grade at the end of the semester, so it is significant. So be working on your homework. Please don't hesitate to email me or to contact me through my WebEx office if you have questions about any of this. All right, so otherwise, have a great week, and I'll talk to you soon.